Hello viewers, good afternoon. Welcome to our channel FlexoMaster, and today we are going to start our chapter number 15, Color Basics and Color Management. And we will cover this subject in 3 chapters. So let's start. What is color? Color is what happens when our eyes perceive different wavelengths of light, which is that part of the electromagnetic spectrum that occurs roughly between 380 and 760 nanometers. A nanometer nm or 1 billionth of a meter measures the distance between the crests of a light wavelength. Wavelengths shorter than 300 nanometers are outside our ability to see them, and they are called ultraviolet or UV. Wavelengths just over 760 nanometers are likewise invisible, and are called infrared or IR. There are lots of other types of electromagnetic radiation like X-rays, microwaves, radar, and radio, and those are also invisible because our eyes and the rest of our vision apparatus are sensitive only to a tiny slice of the energy pi, 380 to 760 nanometers. This is called the visible spectrum, or more commonly just light. See figure 1 here. This is electromagnetic spectrum. The basis of color is trichromacy, which refers to the 3 color channels or receptors of a human retina. What this means in that with only 3 primary colors in either the subtractive or additive color systems, all or most of the other colors can be created. When you add this to the idea of visual blending covered in next chapter, you begin to understand how we are able to print and view color images. With subtractive color, light is reflected off objects that observe some of its wavelength and let others continue on, or our eyes interrupt those remaining wavelengths as a color. In other words, the color of an image on a piece of paper is what left over after the ink and the paper have absorbed or abstracted certain wavelengths. Please see in the figure 2, when full spectrum white light that contains all wavelengths left strikes the sky portion of the print, the red wavelengths are absorbed, and the green and blue ones are reflected back to the produce. The cyan color we call sky blue. All the wavelengths are reflected back on the white cloud since there are no dyes or pigments there. The subtractive primary colors are cyan, magenta, and yellow. The secondaries are red, green, and blue. See in the figure 3, subtractive color here and additive color here. Though the additive color system, which applies to light coming from a computer monitor or a stage lighting, is different in that if you add colors, you ultimately end up with white, not black. The additive primaries are red, green, and blue. The secondaries are cyan, magenta, and yellow. Here, the subtractive primaries in the left and the additive primaries in the right. Notice how the overlaps secondary colors become the primary colors of the other system, and at the same time, the complement of the remaining primary. Here show color is created on computer monitors. Traditional cathode ray tube (CRT) monitors have guns that shoot electron beams toward the inside of the screen, where they strike a phosphor coating. When a beam hits a red phosphor, it gets excited and emits light. of a wavelength perceived or as red. The same things happens with the green and blue phosphors. As the voltage of a gun changes, so does the intensity of the light. Flat panel LCD monitors work differently by using filters to either block the light or allow to it pass. There are no electron guns, instead tiny transistor switches, one each of red, green and blue, sit in front of each screen spot and control the light through polarization. Corresponding to the binary data in the digital file, each pixels on a monitor screen is made up of combination of red, green and blue in varying intensity, 256 level in 8-bit mode. All the other secondary colors come from different combination of values of the three primary colors. As the intensity, brightness of the individual colored pixels increase, they get lighter. Light source and color. Light sources also have their own colors associated with them. That is, you can draw a spectral curve of the light source with each wavelength charted. See figure 4 here. The type of a light source will affect anything displayed under it. And this is where the dreaded word metamerism comes into play. Metamerism, pronounced may, tam, er, ism, is greatly misunderstood as only being a problem with certain types of inks, when in fact it is normal phenomenon relating to how we see color. Metamerism, as when two different color objects have the same color appearance to a normal human viewer under one light source, metameric match, but look different under another light source, metameric mismatch. Since the light source has a major impact on how the colors are perceived, the light along with the object and the human observer form the triumvirate of what we know as a color. See more about light sources and viewing in the room with a view box. Illuminant A, CIE, D65 color white fluorescent. So you will see the differences in the nanometers in metamerism. This figure explains the spectral curves of two different CIE illuminants. A is the tungsten or incandescent. D, or more specifically D65, is a standard daylight source and a popular fluorescent or F source. Measuring color. With standard light sources and a model of human vision, we can measure and quantify the light spectra that form colors in our minds by using one of these three measuring devices. Number one, densitometers. Compute density by directing light into a surface and measuring the amount of light returned through filters. They don't read color directly but can calculate relatively densities of a color patch. Not commonly used of photographers, artists, except in certain situations. Colorimeters measure light through filters like densitometers, but the filters and the internal circuitry match human vision much more closely. Colorimetry standardizes two of the three color variables, light source and observer, and then works with the third object. Colorimeters are frequently used for monitoring profiling. Spectrophotometers, also called spectros, measures the full light of a spectrum in even more detail than colorimeters, either handheld or adaptable to mounting tables or with suction caps. Spectrophotometers can measure reflective prints and in some cases monitor displays and transmissive film. Spectros, including the related spectropolarimeters, are often used in higher end of profiling generating packages. Here, a company called Greg Nachbath instrument the densitometer I1 with the spectrophotometer here showing being used for the printer profiling bundling. Color attributes. One way of defining color is by the three attributes of hue, saturation, and brightness. Each plays an important role and shows up over and over again in the image making process. Hue is a primary descriptor of a color. Red is a hue, yellow is a hue. A hue is the name of that region of the spectrum where most of the color wavelengths dominate. A spectral curve diagram showing reflected red would show wavelengths peaking around 700 nanometers range. Saturation, also called chroma by traditional artists, describe how pure or vivid the color is. Since most real world color combine more than one wavelength, the fewer the extraneous colors, the more saturated the color. Brightness. A primary function of a vision means how light or dark is a color is. These three attributes are visually represented by color spaces, which are next. Now the color space transformation. Color management performs color space transformation from the color space of the image recording device, digital camera, scanner, generally with an intermediary profile connection space to the color space of the output process, offset printing or color proofing or digital printing. Here in the picture shows this is RGB and it is input profile to profile connection space, ICC profiles, CMYK. Color space recording device, then virtual profile connection space, color space output process device. It will be explained again. It must be remembered that the color space of the recording device and the color space of the output process are device dependent. In other words, these color spaces describe the color specific properties of the recording device, digital camera, scanner, etc. and of the print process used pre-press for example, press CTP device, color proofer, monitor to establish a standardized color management process that can handle different input devices and various output channels. A universal device independent profile connection space that links the input profile and the output profile is often interposed. The color spaces themselves cannot be influenced by color management because they are determined either by the physical properties of the devices concerned or in the case of profile connection spaces defined as a universal. Color profiles. This is where the color profiles are. ICC profiles now come in ICC profiles named after the International Color Consortium. Map the color objects during the transition from one color space to the other in such a way that the colors of the originals, example, original photo scene, are reproduced as accurately as possible on the output media. In principle, measurement could now be run on test images for each image source, digital camera, and for each printing material color combination, with the results saved a color profiles in a table of source and target values and return to the color data for each print output. As you can easily imagine, this process would require an extremely large number of profiles and measurement. If you had a large number of input sources and output ways, different presses, printing materials, colors, a profile connection spaces was introduced for this reason, enabling different profiles that are independent of each other to be used for image source, device, and output ways. As a result, only one ICC profile is needed for each input source and for each output process. In a standardized offset print process, and output route going from the import of customer documents, that is PDF files, to screening and CTP computer to plate output up to the press is calibrated in such a way as to always generate the optimal true color print results without having to customize data for each print, exampling control of the press, in addition to color management in pre-press, process calibration, and linearization of the CTP device and press used are a prerequisites for such a standardization to check the standardized print condition and consequently to ensure consistent quality inline camera monitoring. Example, print image in some cases can be used on the press in a standardized print process. This monitoring triggers such automatic readjustment of the color settings of the press if necessary. Processing, calibration and linearization are required to compensate dot gain of the digital dots when imaging to the plate, for example, caused by scattering of the laser beam, and during printing, for example, resulting from different absorptive capabilities of the print material. So, friends, you must have learned the chapter number 15, that color basics and color management we started today, and the next chapter will be on the same subject. And we would like to thank you and kindly subscribe our channel, like and share with others, and you will learn more and more in our next chapters. See you again. Thank you.